Good night. This is a short mini podcast or mini YouTube about the spreadsheet that I promised in lecture this morning. Uh, and that's for an RC circuit, a circuit that has a capacitance and a resistance. And we're going to study the um, discharge function of the capacitor. And it's similar to what the textbook mentions about the charge up procedure or the charge up function for capacitor. Okay, when we finished the regular session this morning, we we pretty much stopped here, and we came to this section after a little discussion of electrons escaping from the capacitor and trying to scamper back to the other side, to the positive side of the capacitor and where they're supposed to be. And how the more that you have, the faster they want to go. And eventually the last electron to leave is going to be kind of pokey. And so we made the deduction that the rate of change of charge in the capacitor, delta Q over delta T, is proportional to the amount of charge in the capacitor. All right. And so if you just have a little bit of charge, your change rate, your rate of change is going to be fairly small. And so there's some kind of alpha, there's some kind of constant of proportionality. That's basically where we finished today. Now, that equation can be rearranged a little bit. Here's the equation, delta Q over delta T equals alpha Q. Just multiply both sides by delta T. And this part over here, you can actually take and program that into a spreadsheet and figure out the evolution of the charge Q of T over time. And that's what we're going to do with a spreadsheet. And so let's go and take a look at the spreadsheet that I've fixed up for you. All right, I spent some time fixing this up and getting it to look nice and everything like that. All right, so the top three rows of the spreadsheet, here they are. You have what you call a time constant, RC, and in our equation, our alpha is actually 1 over RC. All right, and it's in inverse seconds, seconds to the minus 1. And so I said, all right, let's choose for this spreadsheet, to get the spreadsheet to do what it does. We're going to give it a nice round number. So I just said, all right, let's do 2.5. All right. And I said, all right, let's put a nice charge load onto the capacitor for discharge. So, okay, 1,000 coulombs of charge. Nice. Now, one of the things that we're going to do in the spreadsheet is we're going to compute with a delta T. So we have to set up a value for delta T. And so I said, all right, let's have a nice round number for delta T, or in this parlance, dt. And so I just chose 1/10 of a second. All right, so everything's going to work out good. Now, up in the upper right here is, that's the actual time constant. And Greek symbol tau, and it's equal to RC, 1 over alpha. So in this case, that's equal to 0.4, and the dimensions is seconds. There's another time constant related to tau, and it's called the half-life, which you can read about in chapter 31.5 about radioactivity and stuff. And that's, it's a logarithm. It involves logarithms and stuff, and logarithms are going to be coming up in this pretty quickly as we go through this. Anyways, the half-life is related to the time constant tau, and in this situation, the half-life is 0.277 seconds, and I'll explain what that means when we get to the graphs of the charge. All right, fourth line. Here we go. We're going to have a value for time. We're going to start with 0. And the numerical approximation of the charge load Q, we're going to calculate delta Q over delta T with alpha. And then once we get that with alpha, then we're going to multiply by the chosen delta T, and we're going to get delta Q. All right, and so that's how that that calculus equation. That's why I set it up that way. So then in the last column, I'm going to show you the theoretically exact formula for Q of time, Q of T. So the third column is going to be the numerical approximation, and the sixth column is going to be the exact formula. All right, so let's go to it. Let's put in the initial conditions. At time t equals 0.00 seconds, we're just, we're going to say, all right, I've got a capacitor with 1,000 coulombs. And my time constant's 2.5. And it's and what we're going to do is use a negative alpha to represent discharge. Okay, so delta Q over delta T is negative 2,500. That's basically 1,000 times negative 2.5. Right, now when we get that, we multiply by dt, 0.1 second. And that tells me how much charge I lose in the first tenth of a second, negative 250 coulombs. All right, now what that tells me is that at time t equals 0.1 seconds, I've only got 750 coulombs in there now. We've dissipated some of the energy at the resistor, and the amount of charge left is 750 coulombs. All right, so there's the calculation method. Now the spreadsheet's got that all in there. You can fool around with different values for alpha if you want. The third cell in the top row, and you can fool around with different values of the initial charge load. That's the third cell in the second. And if you want to change the time increment, you can do that. That's the third cell in the third row. And then, and the graphs will show it. You might mess up the graphs, but anyways, these numbers lead to a fairly nice graph. All right. So after a tenth of a second, you've got 750 coulombs still loaded onto the capacitor. Now your rate of change is going to slow down because you don't have as many. So let's compute that. All right. 750 times negative 2.5, yeah, 1875. All right. Multiply that by 0.10, and you get negative 187.5 for your delta Q, etc., etc., etc. So you just start calculating away, and you just, and the spreadsheet's the one that does it, and then you start graphing it. So let's do that again, just to double check everything. All right, so here are your settings. Time constant, initial charge load, your delta T, and then over here are just for bookkeeping, so you can take a look at them. You don't really need them to calculate anything, but they're over there for discussion, the two time constants. And then we set up our table, and we start with the initial values, and we calculate the second row. And then once you get the second row, you just do the same thing. Calculate delta Q over delta T again, and then just keep going, etc., etc., etc. Now, this display, this YouTube, only goes down to 0.40, but the actual spreadsheet goes a little bit further, down to 2 point something. All right, and you'll see that in the graphs. So let's get to the graphs. So here's the first graph, and hopefully it looks fairly nice in Microsoft Excel. I don't make any any promises, but hopefully it'll look something like this. Okay, so this is the numerical approximation, and we start up at 1,000. And you'll notice that I have a vertical line for the half-life, 0.28. All right, and that's just for kind of visual comparison. And what the half-life means is for any system like this, the way that it works, there's a certain, once you know RC, once you know the time constant in your system, you can say, all right, there's going to be a time in the future when I've lost 1/2 of what I started with. So that's 500 in this case. Now, if you look at this carefully, you'll see that the numerical approximation, the dashed red line, it doesn't cross the 500 level at 0.28 seconds. It crosses a little bit sooner than that, just like 0.26 or something. All right, so you're right about there. So it's a little bit fast, and the reason for that is we're doing a numerical approximation. It's a fairly nice approximation. Delta t is fairly small compared to the half-life, compared to the time constant. And so we're getting a fairly good approximation. Now, the actual function is an exponential, and you can read about it in the textbook. Here it is in blue. This is the exact solution. And you can see that up in the early stages, they're fairly close together. The blue and the dashed red line are pretty close. And both of them eventually, they both eventually go to 0 as time goes to infinity. Matter of fact, as time goes to 3, they're down there at 1 coulomb. So, but 1 coulomb is still 10 of the 18 electrons. So to have the last electron out, you're going to have to go way out to higher and higher values of t. But pretty much, it's pretty much down to 0 at this point. All right. Now this is Q. This is Q as a function of time, and the current is actually the slope of this. Either one, you can estimate the slope from the. Actually, we have the slope delta Q over delta T estimated in the table, and you can derive the slope directly from the exact formula as well, and it'll look just like this. It'll be another exponential, which is kind of cool because um, that's one of the properties of exponentials. They're self-similar. Anyway, so that's the graphs. So the spreadsheet is pretty good. The textbook mentions e to the minus t over RC, and as your exponential dependence. And that would be the blue line here, all right, with RC equal to 2.5. And so that you can understand why that is the solution. The exponential, why is the exponential system? They don't explain it. They just say, well, you got to use calculus. But this spreadsheet explains why that's the case. You make some approximations about delta Q over delta T and then delta Q and so forth. And you get the red line, and that's pretty close. And the smaller and smaller you make delta T, we used 0.1 second, 10th of a second. But if you used 0.05 seconds, a 20th of a second, your red dashed line would be even closer to the blue line. The blue line would be the same because that's the exact solution. And the smaller and smaller you make delta T, the more of them you need to make your full graph. But it would be closer and closer to the blue exact solution. So that's the situation that we've got. And I didn't do it here. I didn't want to clutter up the diagram, but the time constant tau would be graphed up as a vertical line a little bit further out at 0.4. And I didn't put it in just so that the diagram didn't get cluttered up. But you can fool around with that if you like. If you know anything about spreadsheets, you can mess around with it. All right. Now the spreadsheet that I'm going to post I think in discussions, is discharge-time.dependence.xlsx. I've already got it exported. It looks a little bit, well, this is what it looks like in Apple numbers. Um, and you've already seen it. This is a little bit more of what you saw earlier. You can see the graphs off to the right there. And hopefully you can fool around with it and get some insight of, play with the numbers and whatnot. And that's that. And so what I want you to remember is when you see a situation where your quantity, the time rate of change of your quantity is proportional to the quantity itself, i.e. this equation here, whether it's charge or um, uh, nuclei in radioactive decay or any other thing, anytime you see that, you can make a spreadsheet like what I just described. And theoretically, whenever you see that, you can say automatically that the exact solution is some kind of an exponential. So when you see something like that, it might be a growing exponential, like a biological system. Um, it might be a saturated system like a capacitor that's charging, and there's a function for that in the textbook. Uh, an example of a charging capacitor. That would be what we call a saturation curve, but it's basically exponentials. Exponential decay, which is what we just studied, the discharge curve. You've got, they're all going to have some a version of a time rate of change proportional to the quantity itself. And when you see that, think exponentials of some kind. All right. I'll see you on Wednesday.